One of the things I love about the exponential, the logarithm stuff is that there's so much application to that, and so much so that there's an entire chapter or section devoted to just the mathematics that is involved with finances. We're going to look at a few financial formulas. This first one is on compound interest. You maybe have seen this before. Basically, when you put money into the bank, they will give you a certain amount, an interest rate. They give you money so that they can use your money temporarily. They're storing it for you, but you're basically lending it to the bank. You earn interest on your money for that. Now, the compound part of it, when they compound the interest, that means they actually go calculate how much interest you've earned, and then they put it in your account for you. That's a good thing, because by them putting extra money into your account, all of a sudden now you have more money that you're earning interest on. And the more times they compound it, well, the more money you'll have to earn interest. So you're kind of earning interest on your interest. Depending on what type of an account you have, how often a bank will compound the interest can vary. A lot of it's done it's all computerized, so it maybe is done all the time. Sometimes, if it's in a special CD or some kind of an IRA, it may not compound it as often. Let's talk about this formula. A is your ending amount. As always, that's like the amount you're shooting for. P, this first number, is always that initial value. We call that the principal. The money you put into the account is the principal. This is going to be your growth rate right here. You start off with 1 to account for what you already have, plus this is what you're going to be earning. One of the things we have to be careful about when you see an interest rate advertised, like if it's 7% interest rate, that's an annual interest rate. It's like a 7% APR. That stands for the annual percentage rate. But if they're only going to compound it once a year, then that's a fine interest rate to use. But if they're going to compound it more times, and in this case the formula says this is the number of times it's compounded each year, if they did it every month, then you have to take that annual interest rate and divide it by 12 if it was done monthly, and that would be the monthly interest rate. This always has to be the appropriate interest rate. Then you're going to take it to a power, and this power is the total number of times they compound it. The N, remember, is how many times they compound it per year times T, however many years. That'll be the total number of times they compound the interest. Let's try a problem. I got actually a couple problems. This first one says, what interest rate would double my money in 10 years if it's compounded monthly? What's unfortunate here is they don't give us a starting amount or an ending amount. We just want to double our money. The funny thing is it doesn't really matter if you have $1 and you're trying to double it to $2, or if you have $1 million and you try to double it to $2 million, it's going to take the same amount of time. Let's look at why. Let's make up a number. Let's make it, let's say we have $10 and we're going to put $20. So we're trying to get an ending amount of 20. That'll be my ending amount. My initial amount is 10. 1 plus my interest rate. That's what we're looking for. What is the interest rate? But it's compounded monthly, so I'll have to divide that interest rate by 12. To the N is the number of times it's compounded in 10 years. Let's go solve it. The very first thing you're going to do is divide by that initial amount. Divide by that initial amount. And here's where I was talking about, if you had 1 and you were trying to double it to 2, or 10 and double it to 20, or 1 million and double it to 2 million, you're always going to divide and you're going to end up with a 2 here, every time. Then I have the 1 plus r over 12 to the 120th power. I'm going to have to 120th root both sides, which seems like it's going to be crazy small, but let's see what we get. You'll have to do the 120, and then go to your math menu. That number 5 is doing the roots. And it ends up being a 1 point. Okay, and this is where the decimal points are super important. I'll go ahead and write 0.006, but I'm going to keep the entire value in my calculator. Subtract the 1. And multiply by 12. My interest rate ends up being 0.0695. That probably could easily round up to a 7%, but I think I'm going to go ahead and just call it 6.95% is the interest rate. That would allow me to double my money in 10 years. Let's try the second example. A different type, looking for something else, given different information. How long will it take, so this time I'm going to be solving for t, to turn 4,000 into 5,000 at 8% if it's compounded quarterly? Let's fill in the numbers. The ending amount is 5,000. The initial amount was 4,000. 1 plus the interest rate is 0.08 divided by compounded quarterly means 4 times a year. To the n, it was compounded quarterly times t. I don't know the number of years. That's what I'm looking for. First step, divide by 4,000 on both sides. That's going to simplify to a 1.02 to the 4t. Here's where that solving comes in from yesterday. We need to change this exponential into a logarithm. And divide by 4. Have to use my change of base formula there to do my numerator, and then divide that by 4. I end up with a 2.82 years. So not real long there in order to turn that 4,000 into 5,000. Let's take a look at a different formula. I mentioned earlier that so often banks just look, this is just run on the computer. It doesn't really take a big magic push of the button to compound the interest. It's automatically done. We call that continuous compounding, which is very common. If it is continuously compounded, it's kind of like looking at that previous formula and making that n get bigger and bigger and bigger. You're compounding it more times. You put in a 365, then it would be compounded daily. Well, then maybe you could do it hourly or every minute kind of thing. Well, what ends up happening is it starts to approach a value, and we create this new formula from that, and we affectionately refer to it as Pert. You can see it. The ending amount is going to be equal to the initial amount, the principal, times e to the rt. All the same, the variables all mean the same thing. Let's try an example. I need to invest some money at 6% when my son is born. I need to have 10,000 when he turns 18. Ending amount, 10,000. Initial amount, there's the question. E to the 0.06, and we know that we're going to have 18 years to do this. I'm going to just evaluate in my calculator the e to that power. And I have a 2.94. And just divide. So this was kind of an easy one to solve for the p. I don't have to do any logarithms or anything fancy. 10,000 divided by second answer. The principal would need to be $3,395.96. If I have that much to invest when the child is born, then I'll have the $10,000 when he turns 18. Now, those two formulas on compound interest you'll need to know. Here's a different situation. This is more of a grown-up situation, like when you get your first real job and you decide that you're not just going to like put some money in the bank and then let it just sit there, but you might invest in an annuity. An annuity is where you make regular deposits, like maybe you have a certain amount taken out of your paycheck every month or every 2 weeks or whatever, and it automatically goes into this annuity. You might begin with a big lump sum that you start with, but then you maybe more likely what you're doing is you're just saying, hey, I got my first real job, I'm going to start putting money in. Every paycheck I'm going to put $50 in or something like that. Well, that increases much more quickly because you're adding your own money to it rather than just letting it sit there and gather interest. This is called the future value of an annuity. So let's go through all the different parts of this formula. FV stands for the future value. That's going to be your ending amount. R is your regular payment. That's what you're going to decide to put in I say every month because that's common, but it's every payment period. 1 plus, all right, now here's where it gets tricky. I, this is the interest rate per payment period. You can see this is a crazy formula as is. If you also had to turn this into a little fraction, like on that previous compound interest formula, this is going to get uglier and uglier. We're kind of at the point where we want you to recognize, hey, when we talk about the interest rate, we're talking about per payment period, always. If it's a monthly situation, then you're going to take your interest rate and divide by 12. If it's quarterly, you're going to need to take your interest rate and divide by 4. You have to recognize that you need to adjust it. It will not be given to you. And it's the same I in the denominator. N is going to be the number of equal payments. Again, I'm not telling you the breakdown of it. This is how many times you're going to make payments on it. That means if you're doing it monthly, you'll have to take it 12 times the number of years. You'll have to do a little bit of math problem up there. -1. We're going to look at a scenario using that future value of an annuity formula. We have two situations here. In the first scenario, we're age 25, just got our first real job. You begin putting $100 a month into an annuity at 10% annual percentage rate. How much will you have when you retire at 65? That's scenario 1. Our next scenario is we get to the age 40 and then we begin putting money in. We're going to do, because we kind of started a little bit later, so we're going to put extra money in. We're going to put in $200 a month, still at 10%. How much money will you have when you retire at 65? All right, let's work through both of these situations. It's kind of the same question, just different numbers that we're plugging in. Let's start with situation 1. The future value, that's what we're searching for, is equal to our regular payment, 100, which is not part of that fraction, 1 plus the interest rate. We're going to be paying monthly. We have to take that 10% and divide it by 12. It doesn't come out super nice, so I'm going to store it as alpha I. And then I really kind of want you to write, though, on your paper what it rounds to. That way I know that you remembered to divide it by 12. Don't write I there. Write what the number rounds to. N is the number of payments we're going to make. From the age 25 to the age 65, that'd be 40 years. Times 12 payments a year, I'm going to be making this payment 480 times. All over that 0.008. Let's look at situation 2. Still looking for future value, but now our regular payment is $200. 1 plus the interest rate is the same. but it's not 480 payments. We only had to do this for 25 years times 12. 25 times 12 gets us 300. We're only going to be making 300 payments here. And that is all over that 0.008 number. Go ahead and do the math on this. I probably, if it were me, when I type this in my calculator, I probably would do all of this stuff first and then multiply by 100. Do all of this first, then multiply by 200. All right, go ahead and pause the video and calculate those two things right now. Here's what I got for those two future values. Let's look at what that means. I got $644,000 here if I started when I was 25. If I wait until I'm 40, I only ended up with $289,000. And that's even with me making extra payments here, or higher payments. I think this is worth noting also. How much of this did you actually put? How much of that is your money versus how much of it was interest? Looking at situation 1, I made $100 payments 480 times. That's $48,000 I put into that. The rest of this money is all the bank paying me interest on that. So that's a good deal. Let's look at situation 2. On situation 2, we paid $200 300 times. That's $60,000. In that second situation, we paid more money out of pocket and yet had quite a bit less than half of what we had over here in situation 1. What do you think that means? Okay, I think it has to do with the whole exponential idea that the growth happens towards the end. Things happen slowly at the beginning, but towards the end is when it shoots upward. If you think about this, if you wait and don't start saving money, and you're only going to get the front edge of this. You're not going to get that substantial. If you can do it for a longer period of time, you're going to catch that tail end exponential piece, whereas where you really start making bank. So, the lesson today, invest early. Don't wait and buy that car and get married and buy a house and have kids and pay daycare and diapers and everything else. As soon as you get your very first job, your real job, start that annuity and start saving early. One last formula. This one is on the present value of an annuity. It's a big, hairy, long formula again, and so just be aware that you don't have to have the annuity formulas memorized. The compound interest and continuous interest you do, but I will give you the annuity formulas. The deal is, though, you have to know what all the variables stand for, and you have to know where to plug what. And you have to have used it enough times, you recognize what all the variables stand for. On this one, rather than looking at what's going to happen in the future and doing the future value of your annuity, this is more of a present value, like when you're determining the payments on a loan. If you were to get a loan, you're going to have to pay that back, but you're going to have to pay it back with interest. So there takes a little bit of math to figure out, well, if you have it for a certain length of time, how much interest would accumulate on it, and then what would you have to pay each month to make sure that you've paid back not just the loan, but also the interest. That's what this will find for us. Here's an example. You purchase a new car. It's $16,000. You have in your savings account $3,000, so you put that money down. That means you pay that up front. And then you get a 5-year loan on the rest of it at a 3.2% annual percentage rate. What's your monthly payment going to be? Let's try it. The present value is what your loan is for. Well, the car was $16,000, but since I put down $3,000 up front, my loan is really only going to be for $13,000. My regular payments, well, that's what I'm trying to figure out. What am I going to have to pay every month? 1 minus 1 plus. Now, I is your interest rate per payment period. I'm making monthly payments. That 3.2%, I'm going to have to divide by 12. I got approximately a 0.0027, and I'll go ahead and write that here, but I just stored that value because I'm going to want all those decimal places. I'm going to write 0.0027. And then that needs to be raised to the negative, and remember, n is the number of times or the number of payments that there are going to be. Well, it's a 5-year loan, and you're making monthly payments, so 5 times 12 is 60. So that's to the negative 60 power, and that is all over that interest rate that I have stored, 0.0027. I'm solving for R here. It looks like we just need to clean this whole mess up. We have all this. One of the big mistakes that I see is this R gets put in that fraction. Notice that it has nothing to do with the fraction. It's in front. We can do all of this and have nothing at all to do with the R. In my calculator, you got to be really careful. The hardest part is getting this stuff entered without any goof-ups in your calculator. I think sometimes it's easiest just to do the whole thing left to right in your calculator. The one thing you have to be careful of with this big fraction is that you have to distinguish your numerator from your denominator. I'm going to put an extra set of parentheses around my numerator because I got so much going on. So I'm typing in my calculator, left parenthesis, 1 minus, left parenthesis, 1 plus alpha I. Close the parenthesis to the negative 60, and then close the numerator parenthesis. All divided by alpha I. I ended up with about 55.4. I'm going to divide both sides by 55.4. And I'll have my regular payment. And again, I wrote that, but I'm going to do 13,000 divided by second answer. My regular payment, $234.75. All right. Have fun with these.